So let's continue. One way to summarize the data is to say something about the mean or the median. There is another way, which is orthogonal and is often used. We will, in the exercise we'll do later, we'll ask you to look at some papers, at least one paper, and see what they use. It's important to put a name on what is used. The name here, so we've seen confidence interval for the median, confidence interval for the mean, or for the success probability. Here another thing is prediction interval, which is something used even if we don't do prediction. The idea is if I've received n data points, if I believe that they come from an IID model generated by something that generates a sequence by drawing from the same distribution, one way to summarize it is to say, if I would receive a new data point with probability 95%, in which interval would it be? That's a way to summarize the information I've had from the previous points. That is called the prediction interval. Whether we will really receive a new point or not is immaterial here, so it's not necessarily used for prediction, although we will use it for doing prediction, but it's a means to summarize the variability of the data we see. So formally, it means that having observed x1, xn, prediction interval is something that is constructed from the first n values and such that the probability that the next one lies between those two intervals is large, at least 95% in practice, or larger if you want to be stricter here. It's very similar to computing confidence interval for median or mean. There are practically very similar approaches that are based on the same theories. So the first method is based on what I call order statistic. It's to put in the same bag as a confidence interval for the median, which means it's robust. It doesn't rely on any assumption other than its IID. And it's given by this formula. I take the order statistic, so I order my first n points. I put the n exponent here to recall that we don't touch the last point. And then we look at the table, even though here the table is very simple. I compute indices j and k that are given by that. J is n plus 1 alpha over 2, where alpha is 1 minus gamma here. And k similarly here, and the interval, those 2 points in my ordered set give me the prediction interval. For example, if I have 999 data points, the values of those 2 points will be 25 and 975 here. Which, if you think about it, is quite natural. It means if I have obtained 1,000 data points, and I don't know where they come from, I order them from smaller to larger. I remove 5% of those points, which what we do here by taking those points here, and the next point would lie within those here. What I'm saying is perhaps hand-waving. If you go to the proof that's in the book, you can see that this is formally true. And so that's a very simple formula. For example, we see that if we replace by the mean and the max, that corresponds to the case of 95% confidence interval and n at least equal to 39 here. If we go beyond 39, there is no prediction interval at level 95% here. So if you see only 10 data points, for example, you cannot say anything with confidence 95%. You can say with a bit less confidence, 81%, that you will be between the mean and the max. It's very similar to all the things we've seen so far. It's similar to what can I say about the failure probability when I've seen no failure. It's similar things and similar probabilistic techniques here. So that's the first bag of methods. Again, for some reason that I don't understand, that are probably rooted in history, those methods based on order statistics are not very much used. So if you look at all the papers, even the ones that are done now in data science, people don't very often use that. Right? There was a good reason for not using these things 100 years ago, where if you have a data point with a data set with, I don't know, 1 million data points, ordering them was a dramatic pain, right? Whereas computing the mean could be done by dividing the work into 1,000 clerks that each has 1,000 data points, compute the mean, and we do the means of the means, and we have the mean. Right? For ordering them, it's a bit more complicated. But today, it's no big deal. Therefore, people use another formula, which you have seen very often. The very frequent formula is this one. I have a data set. I want to say something about a hypothetical replay of the experiment. If I would get one more point. Then one formula that we often find is this one. Estimate the mean by taking the mean of the, like we said before, the mean of the first n data points. Estimate also the variance by one of the formulas you prefer. Call S your estimate. And you say with probability 95% will be between mu and plus or minus 196S. So that's very often done. That's even often given as an interpretation of the standard deviation. But of course we know this is true only if the data is Gaussian. So if the data is Gaussian or close to it, we don't have to be fanatic about being strictly Gaussian, but if you, by plotting the histogram of the data, you see something that looks like a bell shape, you can use that. If it looks more like an exponential distribution, this is completely wrong. Right? There's no reason to believe it. So this is true if we have an ID sequence with common distribution that's normal. N here means normal. If we want to be very rigorous, so the major thing here is normal. If we want to be very rigorous, there is even a little catch here, which is the following. That's an important thing that we will discuss again when we do forecasting, for example. If I know exactly the distribution, if I know mu and sigma, then this is a correct formula. Right. But if I have only 10 data points, how do I get mu and sigma? Well, I estimate mu and sigma by taking the sample mean mu and the sample variance sigma squared. And we know there is some uncertainty around it, and we know how to quantify this uncertainty. But if we apply this formula with mu and sigma being itself uncertain, that means we should add a safety margin around it to account for the fact that our parameters themselves are uncertain. This is captured by this formula, formula 233. This one is exact and captures also the uncertainty due to estimation. So we know that the distribution of the new data point minus mu n hat is not the true mu. In this formula, if I would replace mu n hat by the true mu and sigma n hat by the true sigma, and if I ignore the square root in front, this thing here would be what? If I put the true mu and the true sigma instead, it would be the standard normal, because I'm just removing the mean and dividing by the standard deviation. By removing the mean, I make the distribution central. I rescale by dividing by sigma, so I make it standard normal, mean 0, standard deviation 1. So that gives this formula here. What this theorem says that if I replace by the estimated value, I still have a pivot. I have again a student distribution. Therefore, I can say something about this, about xn plus 1. I've measured mu n hat from my n data points, xn plus 1, which is completely unknown, but I know the distribution of this. So I know with 95% probability, this thing will be between the quantiles of the student distribution, which are close to the quantiles of the normal distribution if n is large, but that's another story. So that gives us this result. If I take eta prime the quantiles of the student distribution, then a correct prediction interval is this one. Of course, those two quantities are very close. First, because square root of 1 plus 1 over n when n is large is close to 1. At least at first order approximation, and replace it by 1. And second, we know that the quantiles of the student distribution are very close to the quantiles of the normalized distribution when n is large, and doesn't need to be very large. We've seen that with 30 already the difference is small. Here is an example where I've applied this. I've applied this to a data set, which is the set here. I've measured the time it takes to transfer some objects, and I've obtained this scatter plot here. So on the x-axis is the number of my experiments. On the y-axis is the value I've obtained. If you see something like this, you should react. So the points are not very visible, but they are red. And most of the points are here. What does it tell you? Yes, it says there should be a red light blinking somewhere. I mean, I've plotted this like by using default settings. So what does any default plotter do? It computes the box to accommodate all the data, right? So if all the data lie in one corner, that means there are outliers. There are a few points that are outside, so it's very visible. First take-home message is, if you can, plot your data and look at the data, right? The very first thing to do before doing sophisticated statistics here. So if I do this, this is suspicious. But assume you don't do this. Very often we don't do it because we rely on data science algorithms or machine learning things to give us some result, and we don't look at the data, we just trust the machine to do it for us. Here's what I did. I computed a prediction interval for an hypothetical 101st point, an n plus 1 point I would do. And I computed using the order statistic. This is the interval I obtained here. And I'm showing the median here also. And I'm plotting it, showing another method by computing the mean and standard deviation, which I'm sure if you search enough papers, we'll find lots of papers who do that. We observe the two are very different. We observe that this one is completely bizarre because it gives negative values. So probably if we see the negative values, we would have an alarm somewhere, and we'll dig into it. But what's the true problem?
It's heavy tail, so it's not normal, so we can't read it.
Yes, this is not normal because a normal distribution is very unlikely to have a few very large values, right? So it should have as many very large as many very small because it's symmetric around its mean. So if it would be normal, it would not be skewed like this one. And second, on a small data set that has only 100 samples, the probability of seeing 2 or 3 very large values is astronomically small, so it is highly suspicious. So this interval is probably highly suspicious here. This one is correct if they are truly independent, and reflects the fact that it can be very large, and it is reflected also by the fact that the median is completely not away from the center of the interval. So that is well summarized. So this is perfectly correct and tells you a lot of things. I could have done also a box plot that would have told me a lot about the skewness of the distribution, the fact that it's largely asymmetric here. I think I've already given the answer to that quiz here. So we've discussed that. Of course, this one is a valid prediction interval. It's based on the order statistic. This one is probably not valid because it assumes the Gaussian distribution. It's not assuming central limit theorem, right? It's just for prediction interval, we need exactly Gaussian, right? For confidence interval for the mean, we need only central limit theorem, but for prediction interval, with the standard deviation, we need. So the standard deviation doesn't tell you really much about a distribution unless you know exactly which distribution you're talking of. If you just have some data set, you summarize its variability with a standard distribution, standard deviation, then we have all those problems. One trick that is often used, and that is worth thinking about, is whether we should rescale the data. There's a family of rescalings that is very often used in statistics. That's called the Boxcox transformation, which is essentially a power transformation. So if I have some data X, I standardize it to some per unit value, and I renormalize it around 1, and then I put it to the power s, where s is an exponent that can be positive or negative. So if it's negative, you do the inverse, 1 over x. If it's 1, that's the identity, you don't do anything. And if it's 0, if you do it to the limit of that, that gives the log here. Also, we can do the square if x is equal to 2. Why do we care about that? Well, because it's something that's parameterized with parameter s, we will see that there may be ways to estimate the best parameter that makes it look more normal, for example. Because many techniques work well when the data is close to a normal distribution, a trick that is sometimes used or often used is to rescale the distribution such that the rescale distribution looks more normal. Here is what I did with my file transfer time. I took the log. I did not do a systematic search what is the best exponent, but I took the log, which is a radical means of killing outliers, right? If something is 10 times larger in log scale, it will not look as different here. Of course, it's misleading. A log scale is very misleading, but it gives me this here. So here is the natural value of the data. Here is the log of the data. You see that the log of the data is much nicer, but of course we should remember I've taken the log. Here the log is on the y-axis. Now, here are my 2 prediction intervals I did before. Here I did a prediction of this data in log scale. So in log scale, then it's not quite obviously wrong that it's not normal. The argument I gave before do not apply here, so it seems reasonably centered around, it looks like a cloud centered around its middle. So I could apply a prediction interval in log scale, which is what I did here, and this is what I obtained here. Well, yes?
So then did you transform back the mean, take the exponential of the mean of the log?
That's a very good question. In fact, that's the question I'm asking you now. How did I do this transformation? Of course, we know the mean of a nonlinear transformation is not, the mean is not invariant. The mean of the log is not the log of the mean. Just like the mean of the square is not the square of the mean. Because the difference between the mean of the square and the square of the mean is called the standard deviation. So there is always a difference when we do nonlinear transformation. Now, very concretely, if you have for homework to program in MATLAB this prediction interval here, which is based on the observation that the log of the data looks reasonably normal, how would you do it? And the small majority says C, which is correct. We know that, or we assume, that the log of the data is normally distributed. So let's reason about the log of the data. With probability 95%, the log of the data will be between mu plus or minus 196 sigma, where mu and sigma are the mu of the log of the data, and so I can compute the mu and the sigma of the log of the data. That gives me 2 bounds, u and v. And I know that with probability 95%, the log of a new data, log of xn plus 1, will be between the 2. Now the log is a monotonic transformation, which we can invert, and the inverse of the log is the exponential. So if something is between a and b, the exponential of it is between exponential a and exponential b. The exponential is also monotonic. If it would be the square, we would need to be careful. The square is not a monotonic transformation if the values can be positive and negative. But here, we assume all the values are positive when we took the log, and the reverse, like the log, are monotonic transformation. So if some data point is between u and v, the exponential of this data point is between exponential u and exponential v. So this gives me those bounds here. So I need to compute in log scale, do everything in log scale, and then using monotonicity, have a prediction interval here. back to your question to the mean. So that is what I was saying. That a new data point would be between u and v, y being the log. Right? Therefore, if I take the exponential, that gives me this. Now, if I take the mean of the log, that's the mu, right? If I take exponential mu, what do I obtain? Is it the mean of the data? No. But it has a name, it's called the geometric mean, right? The geometric mean is exactly that. We go to log scale, we take the mean, and then we take the exponential, which we can write with a formula. It's power 1 over n of the product of all the values. So it has a name which corresponds, I mean, the fact that there exists something called harmonic mean and geometric mean correspond to the fact exactly that. The true data that is nice is in a different scale. But when we take the means and we want confidence interval about the means, then it's not as simple. But for prediction interval, it works well. I said before, I assume this looks reasonably normal, but of course this is a bit embarrassing. I mean, it's just based on the expertise of a professor who can say yes, or an expert that says yes, this looks normal or not. How do we do that? There are two ways to do it. There's one tool which is based on the QQ plot and your visual cortex. This is what we'll do now. And there are other tools which are based on tests that we will see a bit later. But both are useful. As usual, it's always very good to look at the data first, because a test gives you much less information than the neural network that's behind our eyes are able to capture when we see things. Right? So what is a QQ plot? A QQ plot is something that's a plot that is used to see whether two distributions are the same. Or more exactly, whether two distributions differ by a linear change of scale. In practice, we use it very often, but not only, with what we call a normal QQ plot. So one of the distributions in the standard normal equals standard Gaussian distribution, and another one is the distribution we have from our data. The standard distribution, we have it in theory, so we can compute exactly its quantiles. So if I call capital F the CDF of the standard normal distribution, the quantiles are given by this exactly. If I have n data points, I compute the inverse CDF of I over n plus 1. Those are the standard normal quantiles. For example, if I have 99 data points, the 1% quantile is the point that corresponds to 1 over 100, and the last one, 1 over, so the 1% will be 1 over 100. And then if I have my data, the other distribution comes from the data, we have seen that the best approximation we can do of the CDF is to sort the data. So we sort the data here. We have x1, x2, xn. And if this comes from that distribution, when n is not very small, the expectation of that is exactly this. So if x is drawn from the distribution capital F, and I do the experiment, do 100 times, produce a sample, sort them from 1 to 100, then the first one should be very close to the theoretical value that's here, and the second one to the one that corresponds to I equal to, etc. That's the theory behind the QQ plot. So what do we do in practice? We plot x, y points where one of the coordinates is given by this and the other by that. So we plot little x, capital X, with the sorted things corresponding to the xi. And this is what I did here, for example. For this data set, I obtain the blue thing here. Now, if both would come from the same distribution, we would have a straight line on the diagonal. Little x is close to capital X. If capital X comes from a normal distribution with mean mu and standard deviation sigma square, it corresponds to a linear change of scale. So we should see a straight line, which is not necessarily the diagonal. but the slope of the offset of the straight line, which should give us the mean and the standard deviation. So the MATLAB QQ-plot formula automatically tries to find, to fit a line, a straight line to this here. That should tell us what are the standard deviation and the slope. But also it tells us whether it is normal or not. So the blue point should be very close to the red line. Here we see they are not. There is a systematic bias. Here the values are larger here. So here, if I look at the x-axis, we see here it's written standard normal quantized, and here it's quantized of input sample. So it means on the x-axis I have the theoretical values, on the y-axis the true values. We see that the true values are much larger than the theoretical values here. So this is the 99 percentile here is much larger than what it should be if it would be normal. It's 200 instead of 102 here. So this distribution has a heavy tail. The large values are much larger than would be predicted by a standard normal distribution, which is what I was doing by hand waving on this plot. I see the cloud is here and there are a few values that are large. We see them here by this tail here that's different. If I do it for the log of the data, this is what I obtain here. So we see that it's reasonably close to the straight line. And by curiosity, I did it for a normal sample. So this is for artificial data, where I asked MATLAB to generate 100 data points from the standard normal distribution, and I did a QQ plot. So I did that to show to you, and in the lab 1, in the lab 2, we will ask you to do also that kind of thing. This shows what statistics is all about. This, if I would obtain exactly a straight line, then statistics and data science would be very simple here. The problem is we don't obtain exactly a straight line. And when do we decide that this is close enough to a straight line and this is not close enough, right? That's the issue. Visually, I would say this is not, this looks fine, but of course we might want to have more quantitative things. We will have them when we discuss tests. We will have quantitative things to decide with probability 95%, are we reasonably confident that this comes from a normal distribution or not? And we'll see that for this sample, such tests will say yes, we can assume it comes from a normal distribution. And they will say no for this one. But take-home message here, if you have such a visibly skewed thing, you don't need to do a test. You do a test if you need it for your paper or your management or your investors or whoever needs to be formally reassured. But the visual thing gives us a lot more information. A small observation, when we have seen lots of things now, confidence interval, prediction interval, and they are confused. You see, when people do data-based things, if they are not very careful, they don't even talk about confidence interval or prediction interval. They say, here is my thing, and this is my estimate, okay, period. If they are a bit more, they have a bit more time, or they're a bit more scientifically minded, or there is more pressure in that community, for example, in the medical science community, if you don't have quantification of the error, your papers are simply not even accepted. So in these communities, you will have, you will need confidence interval. But very often there's a confusion between those two things. If I have a data set, I estimate mu, I estimate S, by one of the two formulas for S we have seen before. If I do this versus that, what am I doing? Here, when I have the square root of n, what I'm doing is in fact finding a confidence interval for the mean, which is very often what we want. We say this thing is in average so much, how much uncertainty is there about my estimate of this so much, which is mean. If I have this thing here, I have another thing which is reflecting the variability of the data also, not just how much. I accept that the data is variable and I would like to know what's the mean. Here is, no, that's not what I'm saying. I say, here is all the uncertainty I have about the data itself. Right? So this one is a prediction interval, assuming it's Gaussian. This one is a confidence interval for the mean, assuming the central limit theorem holds. Observe the difference, which is the square root of n. So this one, of course, is smaller. I will conclude by a small observation that we will come back to when we study model fitting. We have seen different ways. We haven't seen the bootstrap. We'll not talk a bit in this edition of the course, so let's ignore that. But we've seen here ways to characterize the central value, here the median, for a distribution. Here I've simulated a distribution that has an infinite variance. Very easy to do, and we'll see next week how to do simulations of any distribution. Whether it has infinite variance or not, it makes no difference in terms of simulation here. And I've tried, and I've done it with 100 samples and 1,000 samples. What's the difference here? Well, when we have a distribution that has an infinite variance, we have what is called heavy tail. That means one way of explaining why there is infinite variance is that there is a small probability of having very large values. Which means that if I do a small sample, I might see one large value, but not so large. If I do a much larger sample, 100 times larger here, I have a higher chance of seeing larger values. And if I do even larger sample, I might see even larger values. That's the specific of heavy tail and infinite variance. Now for this, assume I want to estimate the median and the mean. The true median is shown on the y-axis here, it's this blue bar, and the true mean is here, it's outside the box. Here I've estimated the standard deviation based on the mean based on the standard deviation. That assumes that the central limit theorem holds, but the central limit theorem holds if the standard deviation is finite, because we estimate the standard deviation and we divide by it. If the true value is infinite, probably there's a problem somewhere, it shouldn't work, and it truly doesn't work. We will see what to do for such cases, but we have seen another thing to do is don't estimate the mean for such cases, and we see that in reality, yes, the confidence interval we have is very wrong here, the true value is completely outside. If I have a very large number of samples, the confidence interval is less wrong, the true mean is inside, but we see that we need a very large number of samples. In contrast, for the median, that problem doesn't exist. The median doesn't make any assumption on the variance. Because in the median, we have the histogram of things. So even if one value is very large, if it's the largest, it is excluded from the intervals we compute when we have all those estimations. So we see that the true median is correctly estimated by the confidence interval for the median. And in fact, when we have 10,000 data samples, the confidence interval for the median is extremely small, and the true median is in it here. Those bootstrap estimates will drop it here. Here's another way of looking at it. Sometimes we can consider that our distribution is heavy-tailed and therefore generates very large values. But sometimes those very large values are simply outliers, measurement errors or external factors that have caused the value to be abnormally large. What is the impact of this on the estimate we do? Well, here is the data that we had before without the outlier, the QQ plot that I've seen before, and the log of the data. So I'm just repeating what we've seen before. Now, I add one outlier that had been removed here. Right? So when the outlier is added, we see that the QQ plot doesn't really, if I have a single outlier, will not really do much. But my estimates, what is the impact of my estimate of the mean and the median? Well, so blue is with the outlier present, red is with the outlier removed. There are several techniques for removing outliers. One of them is, for example, to compute a prediction interval and removing at confidence level very high, for example, 99.9%, and then removing all the values that are above this, or screening them to see whether there were particular cases here. So here I've removed the outlier in the red and kept it in the blue. We see that the confidence interval for the median is not affected, But look at what happened for the confidence interval for the mean, right? One single value being added or transformed, the value itself of the mean is dramatically changed, and the confidence interval for the mean is also dramatically changed. And the same holds for prediction intervals. If you use prediction interval based on order statistics that are independent that are robustness to distributional assumption is also in practice translated into robustness against outliers. That's the take-home message to remember here. Here we see that the prediction interval, by just having one outlier, is dramatically impacted. If I had done it in log scale, so in log scale, the outlier is much less of an outlier. So the problem goes away largely by doing it in log scale. But in log scale, what we're estimating now is the geometric mean. So the estimator of the geometric mean will be okay. Take-home message. If you use those things based on mean and standard deviation, you need to take care, you need to have an outlier processing. You cannot simply apply those methods in some automated tool for estimating, I don't know, in a smart grid, estimating the measurements by removing noise based on those methods. If you use those methods that are very influenced by single outliers, you must have mechanisms for what is called, in some contexts, bad data detection. That may inherently not be needed if you have robust techniques based on median and order statistics. So 20% still believe that it's by intellectual laziness, which might be right, and 60% believe it's because they are easier to compute, and that is probably the good argument. When we need to compute summarized data, then this can be easily aggregated, as I discussed already. This is true not just for computing the mean, but we will see other techniques for model fitting that are based on least squares. All those formulas are very easy to compute. So this might sometimes be important, but the take-home message is if you must use them, or if you choose to use them, be sure you have a bad data detection mechanism in place. Voila, that's all we will do for today. I think I'm fine with time, so we don't need to do a lecture tomorrow. So tomorrow we will do a test at 1:15, followed by the lab, so homework, finishing the programming. And the program of the test is everything we see now, and everything you will learn from now and tonight, between tonight, by doing the exercise on the confidence interval computation. We will be in the room for answering questions, and at the end of the session I will post the solutions also for this exercise today. Thank you very much.